We have seen the foundational concepts of probability and are now able to move on to the more interesting and more practical stuff. So we are going to start a new topic today, which is the concept of random variables. Oftentimes we are interested not in the outcomes themselves, but some mapping of those outcomes to some numbers, numeric values or variables, right? So why? Let's start with an example. So if we have a six-sided die and we roll it, we are going to have a constraint on it which says that the output that you can get is between 1 and 6. So your dice throw is going to be mapped to a number. So your event, whatever the set you have, so let's say 6, this is going to be mapped to an integer n, right? So its type is going to be an integer. Another example would be if you throw a dice twice, you're not interested in the event of, let's say, 1,6, right? So this is the result of two rolls. You're not interested in 1,6. You're interested in their sum, for instance, right? So you're playing a game and you're only interested in the sum. So this event gets mapped to this one individual number, and this number is going to be saved into what is called a random variable. Okay, so since we are talking about the concept of a variable, there is a slight difference between the concept of mathematics variable and the variable of computer science or programming. So let's see what that difference is. So in mathematics, a constant is something that never changes, right? So for instance, pi or e, they never change. A variable in mathematics is something that is assigned once and then it doesn't change afterwards within that one problem. For instance, if you initially say x is equal to 3, that is going to remain 3, because if you later on change this to, for instance, 5, you can go ahead and prove nonsensical statements such as 3 is equal to 5, right? So a variable in mathematics does not change. There is no such thing in mathematics that always changes. Well, there are in some variants of mathematics, but generally when you do high school algebra, things do not change. Okay. In programming, on the other hand, you have constants are the things which are assigned once and then they never change afterwards. Variables are something that we routinely change. For instance, we can say x is equal to 3, and a little down the line we can say x is equal to 5, and then x is equal to 7. In some language we can even say x is equal to string, right? So some sort of a string. So it changes very easily. So what is this random variable that we're talking about over here? It's somewhere in the middle over here, right? So it has the possibility to change, but under very specific values. Okay. So random variables are over here. So what is a random variable? It's a variable that can take on a value from any set. For instance, our dice roll can go from 1 to 6. Each value has a probability associated with it. For instance, our dice roll, which we are going to save in the random variable capital N, can have the value from 1 to 6. Okay, single dice roll. It's also going to have a probability associated with each value. This is how it's typically written, and this is what you'll find in literature. So we're going to follow the same convention. So the probability that the capital N, which is the random variable n, takes on a small value n. So these are going to be n is equal to 1, n is equal to 2, and so on up to n is equal to 6. That's just how we write it. So the probability that the random variable n, capital N, takes on the value n, small n, is equal to, since this is a fair dice, it's going to be 1 over 6 for all the values. Okay. Other examples are, so if you pick any person and measure their height, so this is a random variable which takes on a real valued output. We can also have, for instance, pick any character and convert it to its ASCII equivalent. So that's another random variable. Whatever the ASCII equivalent comes out, that is going to be a random variable. So you can have very large set of things that can be represented using random variables. So whenever you have some event and you map it somehow to some sort of a number, right? So it can be a real number, it can be an integer, or it can be a complex number, anything, right? So that's going to be a random variable. We are only going to be limiting ourselves to integers and real values. Okay. So let's go ahead and see what the probability looks like on a graph. So this is n, this goes from 1 to 6, and the probability stays at 1 over 6. Why are all of these at 1 over 6? Because they are equal, right? So it's a fair dice. So we are going to say that the probability, the whole of one probability, is distributed in these 6 pieces. So each piece is 1 over 6. Okay. Now, This is very similar to the histogram that we saw earlier, but you'll notice that there is a slight difference. There is a gap over here. And the reason for that is this is a bar plot. This is not a histogram, right? So these are disconnected values. Now, this thing that we have drawn over here, we have taken the whole of the probability of 1 and we have distributed it among the different values. Therefore, this thing is called a distribution. For instance, if we have a 20-sided die, it's going to have values going from 1 to 20, and we are going to take the whole of 1 and divide it into 20 equal parts if it's a fair dice, and therefore we are going to have individual probability at 1 over 20. So since we are distributing the whole of probability into different parts, this is called a distribution, and it's one of the fundamental concepts of practical applied probability, and we are going to build on this a lot. So we are starting in this lecture and we're going to do this for a couple of lectures. So n is a discrete random variable. It's a random variable, we've already seen that, and it's discrete because it takes on discrete values. And we've seen what the difference between discrete and real values is. So this is a discrete random variable which can take on values from 1 to 20. Another example, let's go ahead and say that we are going to measure ages of 100 people, and let's say, so this is age. So people of ages up to 10 were 5, from 10 to 20 were 20, from 20 to 30 were 40, from 30 to 40 were 30, and from 40 to 50 were 5. So that turns the whole of 100. Okay. So what we're going to do is we are going to plot their frequencies over here. So at 10, we are at 5, at 20, we are at 20, and so on. Okay. So we plot this. This is called a frequency table. So frequency table, and this is called a frequency distribution. Again, because we are distributing the frequency. We can also go ahead and change these units so that the whole thing turns into a probability. That's fairly easy to do. So we do 5 by 100. So this 100 comes from the total. And 20 by 100, 40 by 100, 30 by 100, and 5 by 100. Right? So that is going to turn this into a probability. What is the probability that the person you pick is between 20 and 30? That is going to be this guy over here, 0.4. Okay. This is termed as the probability frequency distribution, or PFD. Okay. So because it's a probability which comes from the frequency. Okay. We can also go ahead and do what is called the cumulative frequency. It's not that important, but we'll do it for the sake of completeness. So what you do is, so instead of writing people from 0 to 10, you write people up to 10 are 5, people up to 20 are 25. So 5 from this range and this guy over here as well. So we are doing cumulative frequencies. So up to 30, we have 25 from these, or 40 from here, and so on. Right? So similarly, you can go ahead and change this to a probability by dividing all of them by 100. And you will notice that because this covers everybody, this is going to come to 1. If you plot that, you get this, which is called the cumulative frequency distribution, or CFD, right? So we don't typically use this. It's not all that important. We are going to be dealing with this concept over here. Okay. Now let's go back to our original problem of the dice. So if we have a 20-sided dice and we ask a different question, what is the probability that n is less than or equal to 10? Because they are all equal, what we can do is we can apply the sum rule of probability that we saw earlier. We can simply sum all of them together because they are mutually exclusive. If you get a 3, you don't get a 2, and so on. So you can simply go from 1 to 10 and you add the probabilities that n is equal to I. So this is where this notation comes in handy. So the probability that the capital N is equal to small I, and I goes from 1 to 10. So this is going to be summation I is equal to 1 to 10, and this is going to be 1 over 20. So that's 1 over 2. Okay. So that was fairly straightforward. Now note that P of n is less than or equal to 20 must equal 1 because this is a distribution. It's distributing the whole 1 among all of these values. So the whole of them combined must equal 1. That is the basic probability axiom again. We also note that the probability of n is less than 1 must equal 0 because it's simply outside the domain of this random variable. Okay. What happens when we have two random variables? That is where things start to get interesting. So please go back and review this once so that you understand what the distribution is. It's a fairly straightforward concept, but make sure that you let it sink in. In the next video, we are going to take a look at how we can deal with two random variables, and that is going to allow you to reason with very important real world concepts.